Okay, we're going to switch gears and we're going to head into chapter 13. So far, we've been looking at functions like vector functions or parametric equations where you have one input, maybe like t, and then multiple outputs, one for each coordinate or component. So, so one single input, multiple outputs. We're going to see the flip side of this and look at what kind of ideas of calculus could be extended to a function that has uh, multiple inputs. So a function that depends on multiple things at the same time. And then can we still use these ideas about calculus to say things about these functions? So let's get right to it. Okay, so here's a simple picture kind of I have in mind when I think about multiple variable functions. So in the domain, there's multiple uh, numbers you can plug in. So here I just pictured two, x and y, but of course you could have more x, y, z. I know alphabet runs out there, but you could have more variables, right? W, st, just throw them all in there. And then there's only one single output range. So because multiple uh, variables are difficult to picture, most of the time I'm going to draw with two inputs and one output, but all these ideas could be extended to higher dimensions as well. Okay, so um, let's look at some examples so we can kind of get a handle of what kind of functions we're really talking about. So the simplest example I can think of multiple uh, inputs is the addition function. So you can plug in two different numbers and then you're going to add them, and the output is the sum of the two numbers you input. So you've been doing this all your life, right? Like you add two numbers together. We usually think of two numbers being added together, or maybe one variable and a constant like x plus 2. But you could have both of the uh, numbers that are being added to be a variable as well. Okay. So more practical example of a multivariable function is the sunrise function. So um, like what time does the sun rise today, for example? So that depends on where you are and when it is, right? So your sunrise time depends on your longitude, latitude, so your location on Earth, and also what time of the the year it is, right? So let's look at what it is for us. Okay, so this is sunrisesunset.com. Okay, let's look at what it is in Tacoma today. So, all right, USA, and we are in Washington. Okay, and let's look at Tacoma. Or but if you have your own hometown that you want to check out, you could do that as well. So Tacoma here. Month, let's look at April 2021. It's fine. Let's make the calendar. Okay, here we go. So for us, it's April 29th. So sunrise today is 5:57 a.m. So it just kind of got earlier than 6 a.m. I guess a couple days ago. So that's an example of a multivariable function. All right, let me get back to my notes here. All right. Another example that some of the students might appreciate is Cobb Douglas production function. So this is a model that's used in business, but roughly speaking, it's a function that kind of models how much production you can get from what kind of investment you're making. So for example, two variables that matters on how much stuff can get produced is the amount of labor. So like how many people are you hiring? How long are they working? And so on. So the resources that go into labor and also the resources that go into maybe uh, equipment, right? So if you have a more functional, efficient machine, then maybe you can produce more quicker, right? So the two variables here is the labor and the capital that you could invest in your facility company. And for the reasons I don't understand because I haven't taken business classes like this, roughly the amount of production that could be outputted is modeled by some constant. So you could just think of B as one, or like, if you want to think in terms of percentage, like you could say 100%. And then somehow the labor and capital invested kind of grows in an exponent that kind of adds up to one. So some exponent alpha here, it's between 0 and 1, and 1 minus that exponent is there for the capital. Okay, so an example of what this function might look like is if the b is 1 and alpha is equal to 0.75, so it's 3/4, then the exponent for the capital K is going to be 1 minus 0.75, so it's 0.25. So if you think your situation is modeled by this exponent, then you can kind of try to invest in a smart way, right? Like you wanna put where your resources that's gonna increase the production. So is it better to invest in labor where you're at, or is it better to invest in equipment? So that's an important function. And the domain is different values for L and K you can input. So you could think of this as both positive quantities. So the domain will be the upper the first quadrant of this LK axis. Okay, so I shaded the first quadrant there. And that's the domain. I hope that made sense. If there's a business student here, you can correct me. Okay. So looking at the domain and making graphs of these things is not easy. So let's do some practice. Okay, so let's look at a function g, square root of y minus x squared here. So the domain is any number x and y's that I can plug in here for which the function makes sense. So I want the output to be a real number. So I have to have a non-negative number inside of the square root, right? I can square root 0, and I can square root positive number, but I can't square root negative number and get a real number. So we need, for the domain, we need y minus x squared to be greater than or equal to 0. Okay. So what does that domain look like? Well, it might be a little easier if we rewrite this inequality this way. So so bringing the x squared over to the right-hand side by adding x squared to both sides. we get y is greater than or equal to x squared. Still might be a little bit weird to graph, but we know how to graph y equals x squared, right? So y equals x squared is a parabola. So it looks something like this. And y is greater than or equal to that curve. So if the y is greater, that means we're looking at above, right? I can shade in above this curve. And that's going to be the domain for this function. Okay. So its domain is not set of number. It's not like an interval or anything like that. It's a region in xy plane here. Okay. Let's do something that's a little bit harder. So now I wanna graph this. So what we're gonna do is to lift it into 3 dimensions. So there's 2 input variables, x and y, and the z is the output. So if you kind of imagine this domain xy axis gets transferred to the floor of this xyz axis. So if you kind of try to draw it, that's the parabola, and y is greater than that. So this is the domain we're looking at. And higher the output, the higher the height of this graph is going to be. So it's a little bit hard to think about, but it is doable if you think about it maybe 2 dimensions at a time. Sorry, 2 variables at a time. So what we're going to do is we're going to use the technique of level curves. So instead of trying to understand this function all at the same time, we're going to look at, well, what kind of input values will correspond to a certain height. So for example, if we substitute 0 for the output, okay, we could square both sides of the equation, bring x squared to the other side, and we get the parabola y equals x squared. So that's on the boundary of the domain. So this blue parabola that I drew there is part of the graph. Okay, that's on the floor on the xy plane. Okay, what about different height? Well, I don't want to do this for every single possible output, so maybe I'll just put C for constant for the output. So I'm thinking of C as not a variable, but just a constant, fixed number. And we could do the similar thing here. We could square both sides, bring x squared to the other side. Okay, so what is this telling me? Well, it's telling me that level curves, so if I fix the height at C, the x and y values that correspond to that height is going to be a parabola, y equals x squared plus that height squared, right? So I'm going to try to draw them in this picture here. So that's the height 0, 1, 2, 3, 4. Okay, if c is equal to 1, so that's at height 1 above the xy plane, then we're looking at y equals x squared plus 1. So it's the same parabola, but shifted 1 unit in y direction. So maybe a parabola that looks like that. If I set c equals to 2, it's again the same shape parabola, y equals x squared, but then plus 4. So it's shifted 4 units in y direction. Maybe it looks more like this. Okay. And then you can see the pattern on this. So it's always going to look like parabola if you slice it at a particular height. And it's always going to be the same parabola shape, except higher we go, more and more we shift it into the y-axis direction. Okay, this isn't the entire graph though. So if you kind of imagine this as a wireframe, imagine kind of taking a blanket and then kind of wrapping it on top of this wireframe. So the actual surface is going to look something like this. Yeah. Trying to shade it so maybe it's easier to see. I don't know if you can see this. I'm kind of chopping it off at a particular y value so you can kind of see the m side, but it looks like I don't know. I don't know what it looks like. um, actually, this looks like a paraboloid that's kind of opening up towards the y-axis. I hope that makes sense. So if the full paraboloid is like this, then we're just kind of cutting it in half and just looking at the top half. And that's what we have left. Okay. So that's the picture there. Let's practice a little bit more. I think that'll do us some good. Okay, so a couple more functions. So this next one is a little bit easier. Z equals to y minus x. So let's use the same technique. Let's first understand the domain first. So you can plug in any x and y here. You can plug in any real number y and x here, and you could subtract them. So domain is everything. Okay, so the range is also everything, right? Yeah, and then describe the graph. So I'm gonna start using the level curve idea again. So instead of the output z, I'm gonna write c. Okay, so what does this look like? Well, these are lines, right? Y equals mx plus c. Sorry, mx plus b is how we usually think about it. And m, the slope here is 1. And then we have c. So that's the y-intercept. Okay, so the level curves in the xy plane looks like this. Parallel lines, all with slope 1. Sorry, these are supposed to be straight lines, not, I know I drew it the same way as shading. But these are supposed to be lines. So let's see if we can graph that. Okay, so this is x, y, and z. And here's the x equals to, y equals to x line. As we increase the height, we shift this more towards y. So this is a really hard, difficult perspective to draw. But roughly, the surface looks like this, which looks like a plane, right? And it actually is a plane. Another way to look at this problem is that we have z is equal to y minus x. Well, if you bring x and y over to the other side, we get x minus y plus z equals to 0. This is an equation of a plane. So if you recognize this as a plane, then we could have drawn it in a different way, right? Maybe we could spot it a point that he passes through, like the origin, and look at the normal vector of 1, -1, 1, and then look at a plane that's perpendicular to that normal vector. All right. So the vector stuff that we've been doing earlier is still useful in this new setting. Let's do another one. Again, this is a square root thing. So the inside have to be non-negative for this to make sense. So the domain is anywhere where 25 minus x squared minus y squared is greater than or equal to 0. That's a little bit harder to look at, but what if we bring the x squared and y squared to the other side? If we look at this as equals, like x squared plus y squared equals 25, that's an equation of a circle of radius square root of 25, so that's 5. So the domain, or at least the boundary of the domain, is the circle of radius 5. Okay, and then we're looking at 25 is greater than or equal to x squared plus y squared. That might be a little bit harder to think about. But let's see, we're looking at 25 or smaller, smaller radius, right? So we're going to shade in the inside. Okay. And if you were not sure if you should be shading in the inside of the circle or the outside of the circle, what you could do is you could just kind of test a point on the domain, right? So if you plug in x and y equals to 0, that's the origin. 25 is greater than or equal to 0 squared plus 0 squared. That's true. So that's inside of the domain. If you had to pick the point outside, maybe like 100, 100, then 25 is not greater than or equal to 100 squared plus 100 squared. So the outside is not part of the domain. Okay. And we can look at level curves as well. Same idea. You set the output equal to a constant. And move things around until we recognize what this curve looks like. So this is equation of a circle centered at origin with radius square root of 25 minus c squared. So as c gets larger and larger, the radius shrinks. So I'm kind of running out of room here. So we have circle radius 5 in the xy plane, and higher it goes, smaller and smaller circle radius. So if you kind of try to drop a blanket over this wireframe, maybe you see something like a hemisphere, and that's what this looks like. Okay, all right. More practice is needed, really, to get good at recognizing what the graphs look like. But I think this is where I'm going to end the video here. I'll see you guys later.